So I'm going to discuss some ongoing work with my student, Javier Martín García from Madrid. This is stuff in progress. The general idea is to try to introduce notions of holographic complexity which are as quasi-local as possible and that make sort of the point of assigning complexity to singularities, to space-time singularities, okay? So every word in this sentence puts my talk way above the average level of rigor of this conference, so it will be pretty speculative and heuristic. First of all, holographic complexity for me, I mean either of the two Stanford proposals, action complexity or volume complexity, and mostly action complexity for this talk. Fortunately, Rob gave a very beautiful introduction to the whole thing this morning, so I only have to think of the students referring to the singularities in some sense to follow the advice from our chairman at the beginning that we should think of the students for Horacio. I would also want to mention the people who wrote papers on this subject. Now, I'm sure that many of these people are sitting here, and I'm pretty sure that I missed someone, so I should turn around this slide fast. Now, let me just say that in general, on general grounds, we know that singularities are dangerous. You cannot look them in the eye. It's dangerous, because, especially if you're a student, because you can die. But we have seen over the last decades string theory succeed at resolving many singularities, but they are all actually time-like singularities. They are defects that sit there in space-time. They exist in time. And there is a common theme to this business of resolution of singularities in string theory, which is that you always identify light degrees of freedom that are attached to a singularity, and the reason there was a singularity was that you integrated them out illegally. So when you integrate them in and you solve for the light, for the low energy dynamics, then you solve the singularity. And the resolutions look very different depending on whether this process can be taken perturbatively or not. And in some cases, it's just like you see some miracles emerging, like the famous gauge-gravity duality, which can be seen in some loose sense as a resolution of the singularity of classical DP brane solutions. Right? So in this case, something spectacular happens, which is that even the metric in the vicinity of the singularity in a whole region contains sharp physical information about these light degrees of freedom. Now, the situation with the space-like singularities is very different. It's roughly like you substitute strings by theology, basically. So if you like Oriental theology, you would say, well, singularities should be resolved, so life should continue after the singularity, maybe in a similar fashion, maybe repeat itself, something like that. If you are more into the Judeo-Christian tradition, then you would say that they are terminals, because as St. Augustine told us, it doesn't make sense to ask what God was doing before creating the universe, because he created time at the same time as the universe. So it's true that if you think of the black hole singularity as representative of what space-like singularity should be, holography weighs in very heavily into saying that they are terminals, because holography tends to regard the black hole singularity as a terminal, right? But on the other hand, you don't really know if all the singularities should behave like the black hole singularity. There is no classification of qualitative behaviors for singularities or anything like that. What happens with cosmological singularities, we just don't know, right? And this subject, there was a time when people thought about this quite a bit. There's a famous proposal by Penrose, which is the Penrose criterion, which identified, if you like, very ambitiously, a property of singularities that would distinguish them from each other, referring to the degree of order or chaos that they had when you look at the behavior of the metric near the singularity. So if you look at Freeman-Robertson-Walker singularities, they look very ordered. And in particular, a local measurement of that, you could say, is the fact that the Weil tensor is much smaller than the Ricci tensor is actually 0. On the other hand, a typical crunch singularity that could occur in a crunching cosmology you would see this horrible mess of colliding black holes, very chaotic thing. And the singularities, as far as the black hole singularities, the Weil tensor is kind of generic. So you see that Weil and Ricci will diverge at the same rate. So he elevated this to the category of a physical principle, which didn't have much fly because the context in which this was solved was in the context of understanding arrow of time in cosmology. And in fact, we think about the Freeman-Robertson-Walker singularity as resolved by inflation nowadays. So this was not really something that had such a great impact. And on the other hand, you can say that, well, why should you focus on something like the Weil tensor if, after all, this is a low-energy effective field theory concept, and you know that the theory is breaking down near the singularity. So who knows what is the way of characterizing the singularities once you get there, and you have lost control of the effective theory. Now, Penrose did conjecture that there was some connection between this local criterion and some loose notion of the singularity being more or less chaotic. And he talked about entropy basically because of this idea of the collision, the colliding black holes, they would carry entropy, they would merge. So whatever was the entropy that you would assign to this emerging crunching singularity would be measured by the total area of horizons of the colliding black holes. But perhaps a more modern incarnation of this idea would be to regard generic singularities as having more complexity in the holographic sense rather than more entropy. Okay? So this is interesting because the first thing you learn from Rob's talk about complexity, when you take the standard model of complexity, holographic complexity, which is the two-sided black hole, is that there is a difference between, an immediate difference between entropy and complexity. Either if you work in the volume proposal where you are looking at extremal codimension 1 surfaces, or in the action proposal where you are evaluating the on-shell action in some certain Council domains, you find very quickly that asymptotically the complexity grows forever essentially, while the entropy remains constant. Okay? However, it's still true, the advice to the students that they shouldn't, look at the singularities very much because the singularities are out of control. Unless you have very strong tools to deal with them, you are in risk of just saying nothing which is irrelevant. Still, it is remarkable that holographic complexity is the first quantity that we seem to worry about, which actually depends on an evaluation of a low energy term in the effective action at the singularity. Okay? So it's true that extrapolating low energy effective action to the singularity is dangerous, but to the extent that you think that holographic complexity, or at least these proposals like the action complexity, make any sense or capture something which is physical, then you should take seriously the contribution of the singularity because in this case, it's not a small contribution, it's not exponentially suppressed. The singularity contributes a quantity which is in general of the same order as any other term that contributes to the action. This you can see also in very sharp way when you look at how these calculations develop. For example, the famous, the fact that we like, one of the facts that you like about the action proposal is that it shows certain universal behavior in the asymptotic rate of computation in the sense that it doesn't, it has a rate which tends not to depend very much on details like the dimensionality of ADS, the fact that the black hole is large or small, etc. So kind of very neat. And this depends on taking seriously the fact that the contribution of the singularity of the Gibbons-Hawking term at the singularity, you take it seriously with the factors of 2 and factors of pi for that to happen. Also, there is this phenomenon that when you consider black holes in ADS in dimension above 3, the singularity in the Penrose diagram is bent inwards. And that means that the Wheeler-DeWitt patch at the beginning, during a time which is of the order of, is linear in the dimensionality, gets contribution from both the future and the past singularity. And these two contributions cancel when you compute the rate. So for a while, the black hole is not computing until it it liberates one of the boundaries on the past singularity, and then it gets contribution only from the future singularity. So this is kind of a, it's hard to know if this is important or not, but this is, again, a sharp property which is inherent to the proposal and which has to do with terms that are acting on the singularity. There is a sort of an opposite example when you look at hyperbolic black holes. You can find about it in the work of Rob. Hyperbolic black holes, they come with two varieties. They are either hot or cold. The hot ones behave normally. They compute asymptotically at the standard rate. They get a contribution from the singularity. But the cold ones, they have a Penrose diagram that looks more like a streamal, like a charged black hole. And then the singularities stay away from the Wheeler-DeWitt patch. And in this case, this Wheeler-DeWitt patch can be slided, can slide without any computation, so you get zero computational rate forever for the case of these cold black holes. Right? So that's another curious thing, which is a curiosity of these proposals, which again depends on a term in the singularity being active or not. So these examples should tell you that to the extent that you think that these proposals are serious or are capturing physics, then suddenly you have to think that this term in the effective action is capturing some physics, despite the fact that it's a piece of the Lorentz effective action. Okay? And for the purposes of this talk, I will take, of course, the attitude that it is capturing some physics. And my point is that perhaps at least it is a better motivated criterion than the Weyl curvature to distinguish singularities among themselves and assigning some notion of complexity to them. Okay, so one thing we would like to have is some degree of portability of this criteria because we want to be as local as possible. You can find singularities very far from any situation that you can embed in ADS-CFT. So it would be nice to have some definition or some working prescription in which you would have some quasi-locality to the definition. And a hint of how to do that comes again from looking at the two-sided black hole. If you look, for example, at the volume proposal, which is kind of more intuitive, you find that the contribution to the complexity, the time-dependent part, is obtained just by looking at this part of the extremal surface, which is either inside or transitioning outside of the horizon. The other part of the surface is not doing anything really because its volume is constant. There's a Killing vector outside. And more importantly, even if there was some time dependence outside because you were throwing things, etc., the part of the rate that comes from the time dependence of the volume of the exterior part, you wouldn't really assign to the singularity. You wouldn't say that it's measuring complexity of the singularity. This picture suggests that the part of the surface that is measuring the complexity of the singularity is the one that lies within and on top of the past causal domain of the singularity. Okay? So with this in mind, you can just guess or make the assumption that an interesting quantity to look at is just the quasi-local action complexity for the singularity, which would be just evaluating the action in the past domain of the singularity, without regard of any embedding of this in any asymptotic region. Okay? So this would be, if you like, the analog of the extremal asymptotic surface that exists in the case of the volume proposal, which exists inside the black hole precisely because the singularity has zero volume, and therefore there exists some saddle surface there, some local maximum of volume, which sort of measures the amount of complexity that can flow into the singularity forever in time. Right? In order to get some time dependent, you need some Wheeler-DeWitt patches, and then the natural guess is to just anchor them on the null boundary here and just nest the different WDB patches up to the point that you recover the whole complexity of the whole singularity. So this gives you some time dependence with respect to this null coordinate U. And then there is this codimension 2 surface that appears here. If you make a loose interpretation of this in terms of holographic principle, of a generalized holographic principle, you would say that this surface holds the holographic data. Okay? This would be where you put the Hilbert space whose decoding gives you this interior, the interior of the WDW patch. In the case of the black hole, this has a constant area, And you can think that there is a constant dimension Hilbert space that is accounting for this, and you're just evolving the state there. But in general, this could have an area which could depend on you, and it could either go up or down. Okay. So I'm going to consider, the object that I want to consider is some simple object to start thinking about these situations, which is just the action over the Wheeler-DeWitt patch evaluated on the past, restricted to the past causal domain of the singularity, of the subset of the singularity which is anchored on the Wheeler-DeWitt patch. And then I can allow it to be corrected by a counter term that I will call the entropic counter term, which is just a term which measures the volume of the would-be horizon for that singularity. And the idea is that this term is the analog of the piece of the asymptotic surface that you're picking up at time t, and this term is the analog of the contribution of the transition. In fact, when you do the volume prescription, these transitions have a contribution which is of the order of the entropy measured there, right? So it's natural to add this fudge factor just to count the fact that you don't really control very well what you mean by these points here. So the question is, does this quantity have anything, any property which is interesting? And well, what we found is that in a number of examples that we could compute, we found that it has two interesting properties. So the two interesting properties are the following. The first one is that you can adjust lambda, the entropic counter term, so that this quantity is monotonic, monotonically increasing. Okay? So if there is a threat to monotonicity, this threat can always be the rate, the negative rate of complexity increase can always be cured by adding a counter term with the entropy. So it's never harder than the way the entropy changes. Okay? So that's the statement. The second is that the piece which is extensive on the singularity, which is the Gibbons-Hawking term, the one that is kind of interesting if you want to emulate Penrose somehow and give a criterion, a local criterion for the complexity of the singularity, you can isolate it by some coarse-graining procedure out of this quasi-local definition that I gave you. Okay? So I will explain this very fast. So first, terminal monotonicity. We don't have a general proof of these things. We just have a number of examples in which you can compute everything, and it's just very simple, very elementary. But we consider three classes of examples in which there are three qualitative behaviors for the singularity with respect to entropy. So we have one example in which the volume of the codimension 2 surfaces, the holographic surfaces, if you like, the entropy, is constant, which is black holes. We have an example, various examples in which this entropy goes to infinity, and another one in which it goes to 0. Okay? So first, the first one, which is case 1, is constant entropy terminal, which is the black hole case. In this case, these surfaces have constant volume. And then if there is going to be a monotonicity statement here, it has to come just from the behavior of the action here without any possible cure from the entropy term, because the entropy term is constant, and if this is going to grow negative, for example, asymptotically, there's no way you can just fix it by adding the entropy counter term. Okay? And indeed, in this case, you find that it never does that, so the Gibbons-Hawking term always dominates for any black hole, say, in ADS with any type of geometry for the horizon. I mean, spherical, flat, hyperbolic. So in general, this happens, and you get monotonicity without any regard to the boundary term. Case 2 is more interesting. Case 2 is the case where you have divergent terminal entropy, which means that this volume here goes to infinity, and the physics of this is that of a Coleman-de Lucia bubble. If you have a Coleman-de Lucia bubble, you have a singularity inside. You have a collapsing universe inside with negative curvature, a Friedmann-Robertson-Walker with k equal to -1. But the bubble, of course, is expanding, and therefore the area of the acceleration horizon for the wall of the bubble grows indefinitely. Okay? So this entropy goes to infinity in this case. And well, there are a number of models that you can study within this. In fact, you need If you want to be very specific, you need to do numerics because you need to create the bubble with scalar fields, etc. You can also use the thin wall approximation, but there is a very nice model in which you can just cook everything up analytically and sort of gives you the qualitative behavior of the bubble, which was introduced by these people. It's kind of a generalization of the BTZ black hole. It's just like you take ADS and you fiber a circle over ADS in such a way that the circle goes to zero size at some point, and in such a way that the complete fibration is locally ADS itself. So it's like the Hopf fibration, that you fiber a circle over a two-sphere and you get a three-sphere. Here you do it with ADS. So the upper ADS is a compact version of ADS with a circle, but unlike the Hopf fibration, it has a fixed point, and you get a point where the circle goes to zero size, which is the singularity. And the past domain of dependence of the singularity is just ADS in Friedman-Robertson-Walker patch, Friedman-Robertson-Walker coordinates, times a circle, which is shrinking. The isometries of this can be realized outside as isometries of de Sitter crosses one slice, which then go to the boundary, and therefore this whole model, you can embed it in a CFT living in de Sitter times a circle. So there is a global holographic embedding of this model. And well, when you compute the action of the Wheeler-DeWitt patch here, you find that in this case, the Gibbons-Hawking term is not able to win over the bulk term, which is a negative contribution, and then the whole thing diverges to negative, minus infinity. But the rate of divergence is the same as the rate of growth of this area. So by adjusting the coupling, you can just make the whole thing monotonic. Okay? So this is a case where you need to adjust the boundary coupling. Finally, the final case is the opposite case, more or less, in which this entropy goes to zero. And an example which is very simple of this behavior is that you take just the Kastner metric, which is just the simplest homogeneous metric, Ricci flat with a singularity, which is actually pretty generic because, as shown by Belinsky, Kalashnikov, and Lifshitz a long time ago, typically general relativity singularities, when you look at them very, very locally in the longitudinal directions, they look like Kastner, right? So this is not a bad approximation if this diamond is very small. So in this case, what you find, of course, is that this goes to zero, right? There is no contribution from the bulk because it's Ricci flat, cosmological constant is zero. This is one case where it's very difficult to imagine that you can embed it into ADS or anything like that. The Gibbons-Hawking term gives a positive contribution, which grows, so you get monotonicity for free because the bulk contribution is not giving you any trouble. But if there was a coupling turned on the boundary counter term, you have to be careful because even if it doesn't spoil the asymptotic limit of the complexity, it could make you approach the limit from above instead of from below, right? So if you want to approach the limit from below so that you grow, you need to make sure that the coupling is not big enough. It's not too big, sorry. So you get an upper bound on the coupling in this case, right? So again, you find that the way the rate threats monotonicity can always be fixed by a boundary term. So finally, a couple of words about extensivity and coarse-graining. So the extensive contribution to this terminal holographic complexity is given by the Gibbons-Hawking term, I should say York Gibbons-Hawking term, evaluated at the singularity and gives an extensive contribution. What do we mean by an extensive contribution if the metric is singular there? A definition you can give is the following. You can just take a normal Gaussian coordinate near the terminal set and extract the leading behavior of the volume form, right? So that this metric here has a smooth volume form as you approach the singularity. That I will call the comoving volume, and I will say that the singularity has some comoving volume, right? Then, given this exponent, the Hawking-Gibbons term is computed by taking this derivative, which measures the expansion near the singular set. And then this will naturally be something that will scale like a density times volume in comoving volume. And this density will be finite if gamma is equal 1, will be 0 if gamma is larger than 1, and it will be divergent, will be ill-defined if gamma is less than 1. Okay? Now, if you look at vacuum solutions of general relativity, in vacuum, they have gamma equal 1. So you get the typical thing that we get normally when we look at explicit solutions, which look like vacuum solutions, like black holes, etc. You get an extensive finite contribution from the singularity. Instead, the bulk term for these vacuum solutions gives us an answer which is extensive now in the space-time volume of the Wheeler-DeWitt patch, and its sign is correlated with the sign of the cosmological constant. So if the cosmological constant is negative because you are putting everything inside ADS, say, you get a negative contribution. This is the negative contribution that we were getting before, which was threatening our monotonicity. But you see that in general, this makes the whole thing subextensive over the singular set. If you coarse-grain the singular set and you compute the sum of the complete holographic quasi-local complexities and compare it with the original one, you see that it's subextensive, or maybe I should say superextensive. I don't know how to read this. But, the point is that you get a deviation from extensivity, obviously. But this deviation can be made arbitrarily small if you fine-grain a lot, if you coarse-grain a lot. Okay? So if you go to the limit in which the coarse-graining is very detailed, right, then the contribution from the bulk action goes to 0, because these volumes go to 0, and you get to the Gibbons-Hawking term, right? So provided this procedure is smooth, that the bulk contribution is not blowing up, then you get to extract the Gibbons-Hawking term, the extensive term, I will call it the ultralocal term, from this coarse-graining procedure. So this is very nice because this is a relation between the ultralocal part and the complete complexity, which is very similar to the relation that exists between entanglement entropy and thermodynamic entropy. So if you have entanglement entropy of a system, which is pure, it's 0, but if you give some coarse-graining scale, you can define cells, compute the entanglement entropy in each cell, then sum it, and that's the thermodynamic entropy with some coarse-graining scale, and that's the one that in the limit of detailed coarse-graining gives you the kind of object that satisfies the laws of classical thermodynamics. No? So in a sense, this is the Gibbons-Hawking term in this sense gives a kind of analog of that. It's an analog of the classical entropy. Right? Now, to finish, let me just make some contact with Penrose from this point of view. So let's say that I ask what is the ultralocal complexity in this sense, this classical notion of complexity after coarse-graining of the Freeman-Robertson-Walker solution. Well, then the problem I have is that I need matter because in order to have the Freeman-Robertson-Walker solution, which is collapsing symmetrically, I need matter. And then I have to worry about the contribution of the matter in the bulk term, but you can see, you can estimate dimensionally, by dimensional analysis, what is the generic contribution of matter if you model it by a fluid. And then if you have any matter which is less stiff than stiff matter, you know, anything that has a speed of sound which is less than 1, then the contribution of the bulk term is not significant in this ultralocal limit, and you are left with the Gibbons-Hawking term. And the Gibbons-Hawking term is governed by a density which has critical exponent gamma given by 2 over 1 over W, where W is the speed of sound squared of your fluid. And then precisely if you have something which has ordinary matter with a speed of sound less than 1, this is larger than 1. But precisely for larger than 1, the ultralocal complexity was vanishing. So what you learn is that the ultralocal complexity defined in this way for the Freeman-Robertson-Walker model is 0. So in a sense, this is like the Penrose situation. Okay? You have a quantity which is local on the singularity, which tells you that this singularity is less complex than a generic singularity. A generic singularity locally, in this process of cross-graining, we go to the local limit, which is exactly the same limit that was studied by Belinsky, Kalashnikov, and Lifshitz. And in that limit, everything looks like Kastner. And if you do this for Kastner, you do find a non-trivial normal density of complexity. This ultra-local density of complexity is non-zero. Okay? So in that sense, this emulates what Penrose wanted to do with the Weil tensor, but I think it's better motivated because we make it appear in a sort of a natural way from something that we believe is probably more robust, which is the holographic complexity proposal. Okay? So just to conclude, just to say that some quasi-local notions of terminal complexity can be defined, adapting the action complexity ansatz, but still more work is needed to refine them or to understand what they mean, really. An extensive ultralocal component arises through cross-graining, which is just the Gibbons-Hawking term evaluated at the terminal. And this seems to play a role similar to the Weil tensor in Penrose criteria. Okay? So that's, if you like, the two messages. And I will just part with two unconclusions. Unconclusions means things that we don't understand completely, and that's the reason that we are still working on this. It turns out that if you really take seriously this idea of zooming into the singularity by cross-graining, making the diamonds smaller and smaller, you face the fact that, in fact, if you go through the BKL analysis, you find that the generic singularity actually is not just Kastner. It's just an infinite set of Kastner solutions, which are chaotic, in the sense that the Kastner exponents are taken from some hyperbolic billiard game. So it's a succession of numbers which is chaotic. Okay? And something funny happens, which is that when you compute the Gibbons-Hawking term, you have to regularize the surface and take the limit. But now, since you have an infinite number of Kastner epochs, you have to take into account if there is any rescaling of the extrinsic curvature when you pass from one Kastner epoch to the next. And there is a rescaling. There is a rescaling which is finite, so you don't pay attention to it normally. It's just a number which is less than 1. It's a number which is a function of one of these exponents. But then, if you take seriously the idea that there is an infinite set of Kastner epochs, which probably is not reasonable to do, but if you take seriously this idea, you get an infinite product of numbers which are less than 1, and then the answer is 0. Right? So it's like it slips through your fingers again, and ends up behaving similar to the Feynman-Robertson-Walker one. It's kind of evanescent. Right? So I don't know how to really interpret this, but it's kind of interesting. Maybe it's nothing. Maybe you cannot really push your belief in the Lorentz effectivity theory so much. Right? And the other thing that we don't understand is that if you treat the Sitter future infinity as a terminal set, it's not singular, but it looks like a terminal also. It's a terminal. Okay? Then nothing of what I told you works, essentially. You get infinity in all possible ways. The Gibbons-Hawking term gives minus infinity, the bulk term gives plus infinity, but the Gibbons-Hawking term dominates, so the whole thing is minus infinity. So it's infinitely uncomplex somehow, which is at odds with the ideology that future infinity in the Sitter should contain everything, in the idea of eternal inflation. If you put a scalar field there, the quantum configuration of a scalar field can build with low probability, given infinite time, can build everything. Right? On the other hand, if you look at the Sitter infinity from the point of view of DSCFT, maybe that's the point where you put the whatever Euclidean conformality theory you use to trace back the space-time by RG flow. So maybe that's the point where you should say that it's less complex. I don't know. These are just things that we don't understand. I think they are interesting, but I don't know really if they have any meaning or not. So with that, I stop. Thank you very much.
Maybe I missed your point. So what is this complexity? What is this quantity you are computing?
I don't know. I'm just taking the complexity ansatz, the volume complexity ansatz, and generalizing in a way which picks up only the contribution which picks the causal domain of the singularity. So only the part of space-time which is causally connected with singularity. Okay? So for example, in the case of the black hole, this is basically the complexity of the two-sided black hole because nothing interesting happens outside. But in more general situations, this is something which, in principle, you should interpret it in terms of a hypothetical stretch horizon, for example, outside this horizon. You could put a stretch horizon. You could put a quantum system there, and you say that you unfold the interior as an holographic map from this stretch horizon. But we don't know how to do that in general. So the only thing I'm doing here is to do, if you like, experimental search. I just define a quantity and see if it has nice properties, and tells me something interesting about questions of whether you can assign complexity to a singularity or not. And I think it does.
So to simultaneously push on both of these, if you had a real, consider the instability of the Schwarzschild-like singularity, what the BKL one, into set of null, piecewise null singularities, as Mihaly Stathormos wants to do, or correspondingly, if you try to do de Sitter sort of instability into having these FRW type fragmentations and ended up with a bunch of null boundary segments, would this quantity become, this complexity become something tractable?
You mean that the singularity becomes null?
Yeah.
But normally the singularities, the null singularities get destabilized and become space-like. No,
No, it's the other way, actually. Well, Stathormos wants to claim it's the other way.
Well, I don't know. I don't know.
Okay. Other question?
Sorry, this is a very remedial question, but in Rob's talk, he seemed to need the two-sided black hole geometry to define complexity in various ways. I was just wondering, it's not directly tied to your talk, but just to ask you all, if you had the single-sided case, even in ADS, say from collapse, can you define an analog?
Yeah.
Because, by turning on time-dependent couplings on the boundary, at least for the single-sided case, you can achieve some of these cosmological singularities in the bulk. So,
yeah, in fact,
that might be one way to try and
use
ADS as a crutch to
in fact, the bubble case, the second case is such a case, because you have the sitter, actually. And you can map it conformally to a conformal field theory on a fixed sphere times a shrinking circle. So there you're turning on the energy momentum tensor operator on the CFT. Right? But you can do it with a relevant operator, for example, and then you can have some bubble wall which is just going to the boundary infinite time and killing you there. Right? So that's another way of engineering singularities. All those cases should be covered by the case, what I call case 2 in this classification.
Okay, let's
Thank you.
thank.